When the wind blows, a point on this wind turbine blade traces out a circular path. It has a position, a displacement, a velocity. If the wind speed changes, it has an acceleration. We've learned about all these things in a linear context, motion along a line. Now it's time to look at the rotational context. We will be talking about angular position, angular displacement, angular velocities, and angular accelerations. Let's start by talking about position. I've marked a point on the wind turbine in this photo with a red dot. The way we've been describing position is with an XY coordinate system where this red dot would have an X coordinate and a Y coordinate. Well, if the dot moves in a circle as the wind blows, then both X and Y are constantly changing. It's really awkward to use mathematically, and so we're going to use a different system where what's important is the radius, which in this case is never going to change, and the angular position, which the symbol for that is a Greek letter theta. And I'm going to mark this, theta I, this is going to be the initial angular position. As the wind blows, this point will turn, and at a later time, we'll be able to find that same point over here on the circle. Now again, it's fixed on the end of a rigid blade, and so the radius hasn't changed, but now I have a new angular position. Call this theta final. The distance traveled over here, the one that we would measure in meters or something, is called arc length. And the symbol for that, we usually use a delta S. Now, the angular displacement, I'll abbreviate angle and displacement, is delta theta, so that's theta final minus theta initial. There has to be a relationship between these two things. Well, if we've measured the angle in degrees, then here's how we're going to think about it. If this point went all the way around, 360 degrees, then I can calculate pretty easily how far it traveled because I know the circumference of a circle. The circumference of a circle is equal to the radius times 2 pi. It didn't go all the way around though, but I can figure out the fraction of the angle that it traveled. And the way I would write that is delta theta over 360 degrees. So this is how much of a circle it traveled, and then I'm going to multiply that by 2 pi times r, and that will equal my delta S, my arc length. Well, some people might recognize that if I have a 2 pi and I'm dividing by 360, it's actually a units conversion. Radians are a system of measuring angles where a full circle is equal to 2 pi radians. And so if I take my angle and I multiply it by 2 pi and divide by 360, I'm simply converting that angle into radians. Well, how about we skip that step and we just measure the angle in radians to begin with? So a key here is that we're going to be working in radians. So I made a little star, use radians. If I put this in radians to begin with, then the relationship between the angular displacement, which is delta theta, and the arc length, which is delta S, is that I just multiply the angular displacement by the radius. And that gives me the distance that it actually traveled. It's a fairly simple relationship, and this is the utility of radians. This is what radians were invented for, so to speak. Let's just make some notes on what we've talked about. Displacement we use a delta S when we're talking about circular motion, and this describes something that you call arc length. The SI units for arc length are meters. But if you want to talk about angular displacement, we're talking about an angle, and the symbol that we use for that is a delta theta, and the units are radians. And the whole reason that we use radians are that to go from one to the other, if you're using radians, you take that angular displacement, multiply it by the radius of the motion, and you get your arc length. Let's talk about velocity. Velocity is the vector that describes how fast something's going and what direction it's going in. As this point travels along this radial path, it could be traveling at constant speed, or changing speed. We could calculate the average speed along this path by taking the distance it travels and divide by the amount of time. And so I will say our average speed, just the magnitude, is going to be the distance traveled divided by the time. Well, I already know of an angular analog, a rotational analog to this distance traveled. I could talk about the angular position traveled. So that's my angular displacement, and I can divide that by time. And then I know how many radians are traveled every second by this point on average. The symbol that we use to describe this is a Greek letter omega. It's a lowercase omega, and it looks a lot like a W. I try to make mine kind of extra curly to distinguish from my W's. And again, we're just talking about the magnitude here. So how do the speed and the angular speed compare? Well, let's go back to what we know about how arc length and angular displacement compare. So delta theta, if I multiply that by r, I get delta s. And so delta theta over delta t, the change in angle divided by the change in time, times the radius, well, this is the same thing as the arc length, the distance traveled, divided by the time. So this means that my omega times r equals the speed. So the rotational speed, or angular speed, times the radius equals the linear speed. Now, something that's kind of interesting about this is that if I consider a point that's only, say, halfway out on the blade, where I've drawn this green dot, it actually will travel the same angle in the same time, but the distance it actually travels is smaller because the radius is less. So for different points along this turbine blade, they have different linear speeds, v, but they all have the same angular speed, omega. So you might be saying now, well, that's nice, but hang on. Velocity is a vector. You said you were going to talk about velocities. All right, fair enough. So the velocity, like I said, is constantly changing, but it's not constantly changing for omega, because omega, the angular speed, is just described as far as whether we're rotating clockwise or counterclockwise. So for omega, if it's clockwise, it has a negative sign. and that's the direction. If it's counterclockwise, which is abbreviated CCW, then it's positive. And this is true for displacement as well. If the displacement at the point from the initial to the final is a counterclockwise motion, like it is in my example, then that's a positive displacement. If the displacement of the point were in a clockwise direction, that would be a negative displacement. Let's just make some notes on this. So for velocity, I'm going to describe the speed as having the symbol v. The direction changes if it's moving in a circle. And then the SI units are going to be meters per second. For angular velocity, we describe it as omega, and then a positive omega means counterclockwise rotation, negative means clockwise. The units here are going to be radians or rad per second. And then to go from one to the other, omega r is equal to v. Let's talk about the case where the wind speed might be changing. So not only does this point that I've marked on the turbine go from an initial angular position to a final angular position, but it goes from an initial angular speed to a different final angular speed. We can take the change in this angular speed, divide by time, and what we have is angular acceleration. The symbol for that is a Greek letter alpha. How is angular acceleration related to the more familiar linear acceleration? Well, we're going to use the fact that omega, angular velocity, times r is equal to linear velocity. I'm going to multiply both sides of my top equation there by r. So I'm going to have the change in angular velocity times r divided by time is equal to angular acceleration times the radius. Well, I can replace delta omega times r with delta v. Change in linear velocity with respect to time is equal to alpha times r. Well, this is the definition of linear acceleration. So linear acceleration is angular acceleration times the radius of the motion. Now something we need to be very careful about is that there are actually two kinds of acceleration going on here. We have angular acceleration, which describes how the rotation speed is increasing or decreasing, but this is circular motion, and in circular motion there's always another type of acceleration acting. It points inwards and is called centripetal acceleration. So centripetal acceleration is equal to v squared over r. It's also equal to omega squared times r. You can actually prove this for yourself if you're interested in doing that. So how do we tell that apart from this acceleration which points this way? Well, we call this acceleration, I can't write it now, the tangential acceleration. The tangential acceleration describes how much the rotation speed is changing. And that's related to this angular acceleration alpha. The centripetal acceleration describes the fact that the object's moving in a circle, that its direction is constantly changing. They're different. We always have centripetal acceleration when we're talking about rotational motion, and you may, if the rotational speed is changing, also have tangential acceleration. Acceleration, we're talking about the tangential acceleration, which has a changing direction as the rotation happens. The SI units of acceleration are meters per second squared. Angular acceleration, we use the Greek letter alpha to describe this one. It's going to have units of radians per second squared. To go from one to the other, the tangential acceleration is equal to the angular acceleration times the radius of the motion. And then we need to be very careful. The tangential acceleration is not the same thing as the centripetal acceleration. They're different, and it's important to understand their differences. I'd like to do a quick summary of the variables we've looked at. So linearly, displacement was delta S, that was arc length, and the units we described for that are meters. Angularly, we're talking about a delta theta, a change of angle, and we want to measure that in radians because that's the only way we can get this pretty neat relationship that the arc length is equal to the angular displacement times the radius. Now, linearly, we have a speed, which we describe as meters per second, units-wise. Angularly, the variable we use is an omega, which stands for radians per second. And the relationship of those, speed is equal to omega times r. Linearly, we can have a tangential acceleration, and that's in meters per second squared. The angular symbol is an alpha. The units are radians per second squared. And the tangential acceleration is equal to the angular acceleration times the radius. So there's quite the pattern here for these relationships. And so as a final note here, this all assumes a constant radius. Because that defines circular motion. And that's the end of this lesson.